The word multiverse describes a collection of universes that may exist beyond our own. When we look up at the night sky and see the stars, we are seeing only one small corner of what might be an infinitely larger reality. The multiverse suggests that our universe, with all its galaxies and stars and planets, is just one bubble floating in an endless sea of other bubbles. Each bubble is a universe unto itself, with its own laws, its own history, and its own story written across time and space. Imagine standing on a beach, looking out at an ocean so vast you cannot see its edges. Now imagine that each drop of water in that ocean is an entire universe. That is the scale of the multiverse. The concept of multiple universes is not new to human thought. Ancient philosophers pondered whether other worlds might exist beyond our perception. In ancient Greece, atomists like Democritus suggested that reality might consist of infinite worlds, each with its own arrangement of atoms. Medieval Islamic philosophers considered the possibility of multiple creations. But it was not until the 20th century that physics began to take the idea seriously. Advances in quantum mechanics and cosmology revealed mathematical frameworks that seemed to demand the existence of other universes. What once belonged to mythology and speculation slowly migrated into the realm of scientific possibility, carried there by equations and observations that refused to make sense any other way. Hugh Everett III proposed one of the most famous versions of the multiverse in 1957. His many worlds interpretation of quantum mechanics suggested that every time a quantum measurement occurs, the universe splits into multiple branches. In one branch, one outcome happens. In another branch, a different outcome unfolds. Both are equally real, existing simultaneously in parallel. Everett was a graduate student at Princeton when he developed this idea, and it emerged from his frustration with the conventional interpretation of quantum mechanics. The established view required wave functions to collapse mysteriously when observed, an idea that troubled Everett because it seemed to violate the deterministic evolution of quantum systems. His solution was radical. What if nothing collapses? What if every possibility simply continues to exist in its own branch of reality? Everett's idea was initially dismissed by many physicists. His thesis advisor, John T. Wheeler, initially supported the work but later grew cautious about its implications. Niels Bohr, one of the founders of quantum mechanics, rejected it entirely. For decades, the many worlds interpretation remained on the margins of physics, discussed more in philosophy departments than research labs. But gradually, as quantum mechanics matured and its paradoxes grew more apparent, physicists began to reconsider Everett's proposal. Today, it stands as one of the mainstream interpretations of quantum theory, respected and debated across the scientific community. The many worlds interpretation arises from a fundamental mystery of quantum mechanics. At the quantum level, particles do not exist in definite states until they are observed. Instead, they exist in what is called a superposition, occupying multiple states at once. An electron, for instance, can be in multiple places simultaneously until someone measures its position. This is not merely ignorance about where the electron is. The electron genuinely occupies all those positions at once. Its wave functions spread across space like ripples on a pond. The act of observation appears to collapse this superposition into a single definite outcome, forcing the electron to pick one location. But where do the other possibilities go? What happens to the parts of the wave function that corresponded to the electron being elsewhere? In the conventional Copenhagen interpretation, those other possibilities simply vanish. The wave function collapses. Reality crystallizes into one configuration, and all other potential outcomes cease to exist. But this raises deep questions. What counts as an observation? Why does measurement have this special power to collapse possibilities? Does consciousness play a role? These puzzles troubled physicists for decades. Everett's insight was to realize that the puzzles disappear if we simply accept that all possibilities continue to exist. The wave function never collapses. Every outcome occurs in its own branch of reality, each as physical and real as any other. In the many worlds view, there is no collapse. The universe does not choose one outcome over another. Instead, every possible outcome occurs, each in its own separate branch of reality. The observer also splits, with one version experiencing one outcome and another version experiencing a different outcome. Neither version is aware of the other. They inhabit separate worlds that can never communicate. The universal wave function, which describes all possible states of the entire cosmos, evolves smoothly and deterministically, without any mysterious collapse. It is a profoundly different way of thinking about reality, one that trades the strangeness of wave function collapse for the strangeness of infinite splitting universes. This interpretation solves certain paradoxes in quantum mechanics, but it introduces others. If every possible outcome happens, then the number of universes grows exponentially with every quantum event. Every decision you make, every particle interaction, every photon absorbed or reflected creates new branches. Think about that for a moment. In the time it takes for you to blink, countless quantum events occur in the atoms of your body, in the air around you, in the electromagnetic radiation passing through the room. Each event spawns new branches. The multiverse becomes unimaginably vast, filled with countless versions of you, living out every conceivable variation of your life. In some universes, you made different choices today. In others, you made different choices yesterday, leading to an entirely different present. In yet others, the world around you unfolded differently from the start. Perhaps you were born in a different country, spoke a different language, pursued a different path. Perhaps you exist in a universe where history took a different turn, where wars were avoided or never began, where technology advanced faster or slower, where the climate shifted in different ways. Each variation exists somewhere in the branching structure of the many worlds, all equally real, all equally physical, all evolving according to the same quantum laws. The idea that there are many copies of you scattered across parallel universes is both fascinating and unsettling. In one universe, you chose to listen to this tonight. In another, you decided to sleep early. In yet another, you never encountered this at all. Perhaps you pursued a different interest, met different people, shaped a different life. Each version of you is real, experiencing their own sequence of moments, unaware of the others. The you that exists here and now is just one branch among countless branches, all sprouting from the same trunk of quantum possibility. According to physicist Max Tegmark, there are at least 4 distinct levels of multiverse. Each level represents a different way in which multiple universes might exist, each based on different physical or mathematical principles. Tegmark developed this classification to bring order to the various multiverse concepts that appear in physics and cosmology. The levels are not mutually exclusive. If one level exists, others might exist as well. Together, they form a hierarchy of possibilities, each more speculative than the last, each expanding the scope of existence beyond what we can directly observe. The first level is perhaps the simplest to understand and the most conservative in its assumptions. If space is infinite, which many cosmologists believe it is, then eventually every possible arrangement of matter must repeat. This follows from basic probability. There are only so many ways to arrange a finite number of particles in a finite volume. In an infinite universe, those arrangements must recur. Somewhere far beyond the observable universe, there is another region of space identical to ours, with an identical version of you living an identical life. This is not speculation. It is a mathematical consequence of infinity combined with the finite number of possible quantum states. The distance to your nearest identical copy in a level 1 multiverse is staggeringly large. Estimates suggest it would be around 10 to the power of 10 to the power of 28 meters away. That number is so large, it defies comprehension. To give you a sense of scale, the observable universe is about 10 to the power of 26 meters across. Your duplicate would be a distance away that dwarfs this by factors that themselves dwarf all familiar numbers. To reach such a distance, you would need to travel farther than light could travel in trillions upon trillions of years, far exceeding the current age of the universe repeated countless times. Yet, in an infinite universe, such a place must exist. The mathematics insist upon it. Somewhere out there, in a region of space we will never see, there is another you reading these same words, and not just one. In an infinite universe, there are infinitely many copies of you. Some are reading these words right now, just as you are. Others read them a moment ago, or will read them a moment from now. Still others live in regions so similar to ours that they have the same stars, the same planets, the same history, down to the smallest detail. The scale of repetition staggers the imagination. Every possible variation occurs infinitely many times. The level 2 multiverse arises from the theory of eternal inflation. In the early moments after the Big Bang, the universe underwent a period of rapid expansion called inflation. Space stretched at an incredible rate, smoothing out irregularities and setting the stage for the cosmos we observe today. The evidence for this early inflation comes from detailed observations of the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. The patterns in this radiation match the predictions of inflationary theory with remarkable precision. But in some versions of inflation theory, this expansion never truly ends. While certain regions of space stop inflating and settle into stable configurations, other regions continue inflating forever. Imagine a pot of boiling water. Bubbles form throughout the water, each bubble expanding as steam fills it. But the water between the bubbles continues to boil, producing new bubbles continuously. The eternal inflation multiverse works similarly. Each region that stops inflating becomes a bubble universe, an island of stability in an eternally expanding sea. The space between bubbles continues inflating, always producing new bubbles, always expanding, never ceasing. Each bubble is causally disconnected from the others because the space between them expands faster than light can travel. No signal, no particle, no information can pass from one bubble to another. Each bubble is its own isolated cosmos. These bubble universes can have different physical properties from one another. The fundamental constants of physics, such as the strength of gravity or the mass of the electron, might vary from bubble to bubble. The reason lies in what physicists call spontaneous symmetry breaking. In the hot, early universe, the laws of physics were more symmetric. As the universe cooled, this symmetry broke in random ways, like water freezing into ice crystals with random orientations. Different bubbles might undergo symmetry breaking differently, leading to different values for fundamental constants. Some bubbles might have 3 spatial dimensions, while others have 4 or more. The laws of physics as we know them might be local bylaws, valid only in our particular cosmic neighborhood. In other bubbles, entirely different laws govern the behavior of matter and energy. Most of these bubbles would be inhospitable to life. In some, gravity might be so strong that matter collapses into black holes immediately. In others, the electromagnetic force might not exist, preventing atoms from forming. In still others, the universe might expand so rapidly that no structures can ever coalesce. The vast majority of bubbles would be sterile, empty, lifeless. But in an infinite multiverse, even the rarest configurations appear infinitely many times. Among all the inhospitable bubbles, countless bubbles have the right properties to support stars, planets, chemistry, and eventually life. The Level 3 multiverse is the many worlds interpretation we discussed earlier. Every quantum measurement creates new branches, each representing a different outcome. These branches exist in an abstract mathematical space rather than in physical space. They are not distant regions we could travel to, even in principle. They are parallel realities that share the same physical space but never interact with each other. The only connection between them is the universal wave function that describes them all. From the perspective of any observer, only one branch is experienced. The others are real but forever inaccessible, sealed off by the irreversible process of quantum decoherence. Quantum decoherence is the key to understanding how the many worlds interpretation explains our experience of a single definite reality. When a quantum system interacts with its environment, information about the system spreads into the surroundings. This interaction destroys the delicate coherence necessary for quantum interference. Different branches of the wave function become entangled with different states of the environment, making them behave as if they are separate classical realities. A measurement occurs when this entanglement spreads far enough that the different outcomes can no longer interfere. At that point, the branches have effectively split, each continuing independently. Decoherence explains why we do not observe macroscopic objects in superposition. A cat cannot be both alive and dead because the cat is constantly interacting with its environment. Air molecules bounce off it. Photons scatter from its fur. Heat radiates from its body. All these interactions entangle the cat's state with the states of countless surrounding particles. Within a tiny fraction of a second, decoherence occurs and the branches separate. The alive cat and the dead cat exist in different branches, each interacting with a different configuration of environmental particles, each as real as the other, but unable to interfere. The Level 4 multiverse is the most speculative and philosophically radical. It proposes that every mathematically consistent structure exists as a physical reality. If a set of equations describes a possible universe, then that universe exists somewhere in the Level 4 multiverse. Our universe, with its particular laws of physics, is just one mathematical structure among infinitely many. Other structures correspond to universes with completely different laws, different dimensions, different fundamental particles, different logic even. In this view, mathematics is not merely a tool we use to describe reality. Mathematics is reality. Every mathematical object that can exist does exist as a physical universe. This idea, sometimes called the mathematical universe hypothesis, was developed by Max Tegmark as a way to address the deep question of why our universe has the particular mathematical structure it does. Why these laws and not others? Why these constants and not others? The Level 4 multiverse answers by saying that all possible mathematical structures exist, and we simply find ourselves in one particular structure, because observers can only exist in structures that permit complexity and consciousness. It is the ultimate expression of the multiverse concept, encompassing not just variations within a fixed framework, but all possible frameworks themselves. The inflationary multiverse provides a natural mechanism for creating bubble universes with different properties. When inflation began, quantum fluctuations in the inflaton field created variations in how quickly different regions expanded. These fluctuations were amplified by the rapid expansion, growing from microscopic quantum jitters to macroscopic differences spanning vast distances. Some regions inflated more slowly and stopped sooner, forming bubble universes. Other regions inflated faster and continue inflating to this day. The space between bubbles expands so rapidly that the bubbles can never collide, remaining forever separated by an exponentially growing gulf. Within each bubble universe, the inflaton field can settle into different configurations, leading to different physical constants and laws. This gives rise to what physicists call the string theory landscape. String theory, which attempts to unify quantum mechanics and general relativity. By treating fundamental particles as tiny vibrating strings, predicts an enormous number of possible vacuum states. Some estimates suggest there could be 10 to the power of 500 different possible configurations. Each configuration corresponds to a different universe with different properties. This vast landscape provides a natural setting for the multiverse, with each bubble exploring a different region of the landscape. The string theory landscape arises because string theory requires extra spatial dimensions beyond the three we experience. In the most studied version, superstring theory, space-time has 9 spatial dimensions plus 1 time dimension. These extra dimensions must be compactified, curled up into tiny shapes far too small to detect with current technology. The characteristic size of these compactified dimensions is thought to be around the Planck length, about 10 to the power of minus 35 meters. At such scales, quantum gravitational effects become significant, and our usual notions of space and time break down. But there are many different ways to curl up 6 dimensions into a compact space. The mathematical objects that describe these compact spaces are called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tong Yau, who developed the theory. Each different Calabi-Yau manifold produces different physics in the large 3-dimensional world we inhabit. The specific shape of the compactified dimensions determines the values of fundamental constants, the types of particles that exist, and the forces that govern their interactions. A universe with one particular Calabi-Yau manifold might have weak gravity and strong electromagnetism. Another universe with a different manifold might have the opposite. The landscape of possibilities is enormous. The number of distinct Calabi-Yau manifolds runs into the thousands, and each manifold can be compactified in many different ways. When you multiply these possibilities together and include other factors like fluxes and branes, the number of possible configurations explodes. The figure of 10 to the power of 500 is a rough estimate, and the true number might be even larger. Some physicists see this as a feature, providing a natural explanation for why our universe has the particular properties it does. Others see it as a problem, arguing that a theory that predicts everything predicts nothing. The anthropic principle offers one way to understand why our universe has the properties it does. In a multiverse with countless different configurations, only certain configurations can support the development of conscious observers. We find ourselves in a universe capable of supporting life, not because it was designed that way, but because we could not exist in any other type of universe. The apparent fine-tuning of our cosmic home is explained by selection bias. We observe a life-friendly universe because only life-friendly universes produce observers to do the observing. It is a circular argument, but it is the kind of circularity that arises from necessity rather than error. Our universe does appear to be finely tuned for life. The strength of gravity, the mass of the proton, the energy levels in carbon nuclei, the density of dark energy, the rate of cosmic expansion, all seem calibrated to allow stars and planets and complex chemistry to exist. If gravity were much stronger, stars would burn out too quickly for life to evolve. If it were much weaker, stars might never ignite at all. If the strong nuclear force were slightly different, carbon could not form in stellar furnaces, and carbon-based life would be impossible. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to form. These fine-tuning examples can be multiplied. The neutron is slightly heavier than the proton, allowing hydrogen to exist without decaying. If the masses were reversed, all hydrogen would decay into neutrons, and chemistry as we know it would be impossible. The ratio of electromagnetic to gravitational force is enormous, about 10 to the power of 36. If this ratio were much different, either planets would be too hot or stars would be unstable. The list goes on. Each constant seems exquisitely balanced to allow the universe we observe. The fine-tuning problem has puzzled physicists for decades. Why do the constants have the values they do? Why are they finely tuned to permit life? One answer is that there is no deeper reason. The constants simply are what they are, and any attempt to explain them is futile. Another answer invokes a designer who set the constants with the intention of creating a universe capable of producing life. But the multiverse offers a third answer. If countless universes exist with different values for the constants, then the question of why our universe has life-friendly values becomes trivial. We observe life-friendly values because we could not exist to observe anything else. The many worlds interpretation predicts that you are constantly splitting into countless versions of yourself. Every decision you make, every random event that affects your life, every quantum measurement in your vicinity causes the universe to branch. In one branch, you chose coffee this morning. In another, tea. In yet another, you skipped breakfast entirely. All of these versions of you exist simultaneously, each convinced they are the only version, each unaware of the others. The multiverse branches like a tree with infinitely many limbs, each branch as real as any other. The branching occurs at every moment. As you sit here now, listening to these words, countless quantum events are happening in the atoms of your body. Electrons jump between energy levels. Radioactive nuclei decay or do not decay. Photons are absorbed or pass through. Each event creates new branches. The version of you that continues listening splits from versions that get distracted, that fall asleep, that experience different thoughts. In the many worlds interpretation, all these possibilities are realized somewhere in the branching structure of reality. Some physicists find this picture unsettling. It seems to violate our intuitive sense that reality is singular and definite. We experience one outcome, not all outcomes. We remember one past, not many pasts. We feel like unified beings moving forward through time, not constantly fragmenting into multiple selves. But the many worlds interpretation argues that this is merely a limitation of our perspective. We experience only one branch because our consciousness is tied to a particular sequence of quantum events. The other branches are just as real, just as physical. But they are inaccessible to us because quantum decoherence prevents different branches from interfering with each other. The fate of the multiverse depends on which version we are considering. In the level 1 multiverse, each region evolves according to the same laws, eventually reaching heat death, as stars burn out and black holes evaporate. The far future of such a universe is cold, dark, and empty, with occasional random quantum fluctuations, the only events breaking the silence. In the level 2 multiverse, different bubbles might have different fates. Some might collapse back on themselves in a big crunch. Others might expand forever into cold heat death. Still others might reach a stable equilibrium. The eternal inflating background continues forever, always producing new bubbles, always expanding, never ending. In the many worlds interpretation, the multiverse grows more complex over time but never ends. As long as quantum events occur, new branches form. The tree of branching realities extends forward into eternity, each branch evolving according to its own history. There is no final state, no ultimate configuration, only an ever-growing structure of possibilities, all simultaneously real. Death, in this picture, is not an ending, but a branching. In some branches, you survive hazards that kill you in others. In some branches, medical science advances rapidly enough to extend your life indefinitely. In others, tragedy strikes early. All outcomes occur somewhere in the tree. The concept of the multiverse challenges our intuitive notion of reality. We are accustomed to thinking of the universe as a single, definite entity. We assume there is one true history, one set of facts, one way things are. The multiverse suggests that this intuition is mistaken. Reality is not singular, but plural. There are many histories, many sets of facts, many ways things are. All coexist, each as valid as any other. This plurality is not metaphorical. It is literal. Other universes, other branches, other configurations are as physical and real as the room you are in now. Some physicists have proposed tests that might provide indirect evidence for the multiverse. For example, if bubble universes occasionally collide, they might leave imprints on the cosmic microwave background. These imprints would appear as circular patterns, regions where the temperature fluctuations differ from the surrounding sky. The collision would occur when two bubbles, nucleated close together in the eternally inflating background, and expanded into each other. The energy released would create ripples that propagate through our bubble, eventually appearing as patterns in the microwave sky. Several searches for such patterns have been conducted using data from satellites like WMAP and Planck that have mapped the cosmic microwave background in exquisite detail. Some researchers have claimed to find suggestive signals, circular patterns that might indicate collisions. But none have been confirmed as definitive evidence. The patterns could also arise from random fluctuations or from other astrophysical processes. The search continues, with each new dataset offering more sensitivity and better resolution. If collisions have occurred, future observations might reveal them. Another potential test involves the distribution of physical constants. If the multiverse is real and the anthropic principle explains fine-tuning, then we should expect our constants to be typical among those that allow observers. If we find that our constants are highly atypical, even among life-supporting values, that would be evidence against certain multiverse models. So far, detailed analyses suggest that our constants do appear to be relatively typical. The cosmological constant, for instance, has a value that is small enough to allow structure formation but large enough to be detectable, which is roughly what anthropic reasoning predicts. The multiverse may also make predictions about the future of physics. If string theory is correct, and the landscape contains countless possible configurations, then we should not expect to find a unique theory of everything. Instead, we should expect to find that many different configurations are possible, with our universe being just one example. This would mark a shift in how we think about the goals of physics. Instead of seeking the one true theory that uniquely determines all physical laws, we would seek to understand the space of possible theories and explain why we find ourselves in one particular region of that space. Some physicists find this prospect disappointing. The dream of finding a final theory, a set of equations that uniquely determine all physical laws, has driven much of theoretical physics for decades. This dream goes back to Einstein, who spent the latter part of his life searching for a unified field theory that would encompass all forces of nature. The multiverse, if real, suggests that this dream may be unattainable. There may be no single answer to the question of why the universe is the way it is. The answer may simply be that other universes are other ways, and we happen to be in this one. Others find the multiverse concept liberating. It frees us from the need to explain every detail of our universe as necessary. Some features are contingent, the result of chance or historical accident rather than deep principle. This shifts the focus from explaining everything to explaining what can be explained and accepting the rest as environmental. It is a more modest, but perhaps more realistic approach to understanding nature. Instead of asking why the laws of physics are what they are, we ask what range of laws is possible and what constraints anthropic reasoning imposes on the laws we observe. The mathematical consistency of the multiverse depends on the specific version being discussed. The Level 1 multiverse is simply a consequence of infinite space, requiring no new mathematics. It follows from general relativity and the observation that the universe appears flat on large scales. A flat universe extends infinitely, and in an infinite universe with finite particle types, repetition is inevitable. The Level 2 multiverse follows from inflationary cosmology, which is well established and supported by observations. Inflation solves several puzzles about the early universe and makes predictions that have been confirmed. The Level 3 multiverse emerges from standard quantum mechanics, requiring only that we take the wave function seriously and do not add collapse as an extra postulate. The Schrödinger equation, which governs the evolution of quantum systems, is deterministic and linear. If we apply it to the entire universe, including observers, without adding any collapse mechanism, the many worlds interpretation follows naturally. All that is required is taking the mathematics of quantum mechanics at face value and resisting the temptation to modify it. The level 4 multiverse is the most mathematically demanding. It requires accepting that every consistent mathematical structure corresponds to a physical reality. This is a strong claim, and it raises difficult questions about what counts as a mathematical structure and why mathematics should have such ontological power. Some see it as the ultimate expression of the unreasonable effectiveness of mathematics in describing the physical world. If mathematics is so good at describing reality, perhaps it is because reality is mathematics. Others see it as a step too far, confusing the map with the territory, mistaking our descriptions of nature for nature itself. The many worlds interpretation also raises questions about personal identity. If you constantly split into multiple versions, then which version is really you? All of them? None of them? The question may not have a meaningful answer. Personal identity might be more fluid than we intuitively assume, defined not by a single continuous thread, but by a branching structure of overlapping selves. Each branch has memories of a shared past and anticipates a different future. Each branch feels like a continuous self, unaware that it is one among many. Some philosophers argue that this does not threaten our usual concept of identity. Each version of you has a unique history and experiences a single continuous thread of consciousness. From the inside, each version feels like the one true self. The fact that other versions exist does not diminish the reality of your own experience. You are not less real because other versions of you exist in parallel branches. Your experiences, your thoughts, your emotions are all genuine and irreducible, regardless of what happens in other branches. In the inflationary multiverse, the space between bubble universes expands faster than the bubbles themselves. This means that most of the volume of the multiverse is empty inflating space, with bubbles occupying only a tiny fraction of the total. The bubbles are like islands in an ocean, separated by vast expanses of expanding vacuum. The ocean grows faster than the islands, ensuring they remain isolated from each other forever. The typical distance between bubbles is far larger than the size of any individual bubble, and this distance grows exponentially with time. Within each bubble, the physics can be different. Some bubbles might have strong gravity and weak electromagnetism. Others might have the opposite. Some bubbles might have more than 3 spatial dimensions. The properties depend on how the inflaton field settled and how the extra dimensions compactified. Others might have fewer spatial dimensions, perhaps a 2-dimensional universe with very different geometry and physics. The diversity of possibilities is limited only by the range of configurations allowed by the underlying theory. In the string landscape, That range is enormous, providing ample room for variation. Life can only arise in bubbles with the right properties. The constants must allow for stable atoms, chemistry, stars, planets, and sufficient time for complexity to develop. Carbon must be able to form in stellar furnaces. Water must be stable at planetary temperatures. DNA or something functionally similar must be possible. The universe must last long enough for evolution to produce complex organisms. Most bubbles fail one or more of these criteria. But given enough bubbles, even rare conditions occur infinitely many times. Somewhere in the multiverse, countless bubbles support life, each with observers wondering if they are alone. The anthropic principle helps make sense of this picture. We observe a life-friendly universe not because life-friendly universes are common, but because we could not observe any other type. The selection effect is unavoidable. Only universes with observers produce observations. This does not explain why any bubbles are life-friendly, but it explains why we find ourselves in one of the life-friendly bubbles rather than in a sterile one. It turns a mystery into a tautology. But sometimes tautologies are the best explanations we can hope for. The question of whether other universes exist may ultimately be unanswerable with certainty. We can infer their existence from theories, but we may never observe them directly. Does this make the multiverse unscientific? Some say yes. Science, they argue, must be based on observation. Entities beyond all possible observation are metaphysical, not physical. If we can never see other universes, how can we claim they exist? How is this different from believing in invisible fairies or undetectable spirits? But others point out that many accepted scientific entities are unobservable in practice. We cannot directly observe the interior of a black hole, yet we infer its properties from how it affects surrounding matter. We cannot see beyond our cosmic horizon, yet we infer the existence of distant galaxies from the cosmic microwave background. We cannot observe events that happened before the universe became transparent, yet we infer them from theoretical models that explain what we can see. The multiverse may be no different, unobservable in practice, but inferable from the theories we use to explain what we can observe. The convergence of multiple lines of reasoning toward the multiverse is striking. Quantum mechanics points to many worlds through the Everett interpretation. Inflation points to bubble universes through eternal inflation. String theory points to the landscape through the multiplicity of vacuum states. Each line of reasoning arises independently from attempts to solve different problems. Quantum mechanics was developed to explain atomic spectra and other microscopic phenomena. Inflation was developed to explain the flatness and homogeneity of the universe. String theory was developed to unify gravity with quantum mechanics. Yet they all suggest that our universe is not unique. This convergence is not proof, but it lends the multiverse concept a certain plausibility. The multiverse, if real, would be the ultimate expression of nature's creativity. Every possibility explored, every potential realized, every configuration actualized. The totality of existence would encompass not just what is, but what could be, all possibilities made manifest in parallel realities. It is a vision of staggering scope, humbling in its vastness, dizzying in its implications. The human mind struggles to grasp it, accustomed as we are to thinking in terms of single, definite outcomes. But the mathematics seems to demand it, and the logic appears sound. And yet, for all its grandeur, the multiverse does not change the immediate reality you experience. You still occupy this universe, this moment, this life. The existence of other universes, other versions of you, other realities, does not diminish the reality of your own experience. You are here, now, breathing, thinking, drifting towards sleep. That is a fact, regardless of what exists elsewhere. Your joys are real. Your sorrows are real. Your choices matter, even if other versions of you make different choices. Because this version, the one experiencing this moment, is you. Perhaps the multiverse is real. Perhaps it is not. Perhaps we will never know for certain. The question may remain forever in the realm of speculation, tantalizing but unconfirmable. But the journey through these ideas, the exploration of possibilities beyond our own corner of existence, expands the imagination and deepens our sense of wonder. The universe, or multiverse, is far stranger and more magnificent than we once imagined. And that strangeness, that magnificence, is worth contemplating, even if we can never fully understand it. Consider the implications of quantum branching in your daily life. Every time you make a decision, the universe splits. In one branch, you choose option A. In another, option B. Both choices are made, both realities unfold. Does this mean your choices don't matter? Some argue yes, claiming that if all outcomes occur, then choice is meaningless. But this misses something important. Your choices determine which branch you continue along. They shape the sequence of experiences that constitute your life. Other versions may make other choices, but those are other lives, other sequences of experience. Your choice determines your life, the one you live and feel and remember. In the Level 1 multiverse, your duplicates are living lives identical to yours at this moment. They are reading these same words, thinking these same thoughts, experiencing this same moment of contemplation. The synchrony is perfect because the initial conditions are identical. But in moments to come, quantum fluctuations will cause their paths to diverge from yours. Random events will unfold differently. Neurons will fire in slightly different patterns. Thoughts will drift in different directions. Gradually, your duplicate will become less identical, their life trajectory deviating from yours in increasingly significant ways. How far away is the nearest version of you that made different choices? That depends on how different. A version of you who chose tea instead of coffee this morning might be separated by an unimaginable distance, perhaps 10 to the power of 10 to the power of 50 meters away. A version who never lived in your city might be even farther. The more significant the difference, The rarer the configuration, and the greater the typical distance to the nearest instance of that configuration. Yet, in an infinite universe, all such configurations exist infinitely many times. The bubble universes in the Level 2 multiverse could have different numbers of spatial dimensions. Our universe has 3, allowing for complex structures and rich physics. But other bubbles might have 2, 4, 5, or more. A 2-dimensional universe would be very different from ours. Motion would be more constrained. Complexity would be limited. It is unclear whether life could arise in such a universe. A 4-dimensional universe would also be strange. Orbits would be unstable. Atoms might not form. The inverse square law for forces like gravity and electromagnetism depends on the number of dimensions. And changing this number has profound effects on physics. Some researchers have explored what physics would look like in different numbers of dimensions. In 2 dimensions, general relativity becomes trivial because space has no curvature. In 4 or more dimensions, planetary orbits become unstable, making solar systems impossible. Atoms might not be stable because the electromagnetic potential behaves differently. These analyses suggest that 3-dimensional space is special, perhaps uniquely suitable for complex structures and life. This adds another layer to the anthropic principle. Not only must the constants be right, but the number of dimensions must be right as well. The many worlds interpretation implies that quantum immortality might be possible, at least in a sense. The idea is that in every branch where you die, your consciousness ceases to exist in that branch. But there are always some branches where you survive, no matter how unlikely. From the subjective perspective of your consciousness, you would always find yourself in a branch where you survive. You could never experience your own death because the act of dying eliminates the observer who would experience it. This leads to the strange conclusion that you might be subjectively immortal, always finding yourself in the rare branches where you survive against all odds. But this argument is controversial, even among supporters of many worlds. It assumes that personal identity continues along branches with very low probability, and it is unclear whether this makes sense. Moreover, even if you survive in some branches, the vast majority of branches lead to your death. The measure of survival branches might become vanishingly small, making survival an increasingly rare and unlikely experience. And quantum immortality does nothing to prevent suffering or degradation. You might survive, but in branches where you are gravely injured or diminished. The concept raises more questions than it answers. In the string landscape, the properties of universes depend on the shape of the compactified extra dimensions. These shapes are not arbitrary, but constrained by mathematical consistency. The Calabi-Yau manifolds that describe these shapes must satisfy certain geometric conditions. They must have a property called Ricci flatness, meaning their curvature averages to 0. They must also respect supersymmetry, at least in the simplest models. These constraints limit the possibilities, but still leave an enormous number of allowed configurations. Each Calabi-Yau manifold can be further modified by adding magnetic fluxes threading through its various cycles. These fluxes add additional parameters that affect the physics of the resulting universe. The fluxes can stabilize the size of the extra dimensions and contribute to the vacuum energy or cosmological constant. When all these effects are combined, the number of possible configurations becomes astronomical. Some estimates place it at 10 to the power of 500, though the exact number depends on assumptions about which configurations are stable and which are not. The vastness of the string landscape has led to debates about the predictive power of string theory. If the theory allows 10 to the power of 500 different possibilities, and we have no way to calculate which one describes our universe, then what has the theory actually predicted? Critics argue that this makes string theory unfalsifiable and therefore unscientific. Supporters counter that the landscape is a feature, not a bug, because it provides a natural explanation for fine-tuning through anthropic reasoning. The debate continues, with both sides making valid points. The holographic principle, which emerged from studies of black holes, suggests that all the information contained in a volume of space can be encoded on the boundary of that space. This idea was developed by physicists studying what happens to information when matter falls into a black hole. They found that the information content of a black hole is proportional to the area of its event horizon, not its volume. This suggests a deep connection between information and geometry, with implications for how we think about space and the multiverse. If the holographic principle is correct, then our three-dimensional universe might be a projection from information encoded on a two-dimensional surface. This surface could be at the edge of our cosmic horizon, the boundary of the observable universe. Different regions of this surface might encode different universes, each projecting its own three-dimensional reality. The multiverse, in this picture, is not a collection of separate spaces but different projections from a single underlying structure. It is a radically different way of thinking about multiple universes, one that blurs the distinction between the universes themselves. The simulated multiverse is an even more speculative idea. It proposes that advanced civilizations might create simulated realities, virtual universes running on computational substrates. These simulations would be as real to their inhabitants as our universe is to us. If such simulations are possible, and if civilizations routinely create them, then the number of simulated universes could vastly outnumber the number of fundamental physical universes. This leads to a disturbing possibility. Statistically, we are more likely to be in a simulation than in a fundamental reality. The simulation hypothesis, popularized by philosopher Nick Bostrom, argues that at least one of three propositions must be true. Either civilizations never reach the technological capability to create realistic simulations, or they choose not to create such simulations, or we are almost certainly living in a simulation. If the first two are false, then the third follows by statistical reasoning. The vast majority of conscious beings in such a scenario would be simulated rather than fundamental. But there is no way to definitively test this hypothesis. A sufficiently sophisticated simulation would be indistinguishable from a non-simulated reality. If we are in a simulation, then the laws of physics we observe are merely the rules programmed into the simulation. The constants are parameters chosen by the simulators. Our universe is not fundamental, but contingent. One possibility among many that the simulators could have chosen. They might run multiple simulations with different parameters, exploring different regions of the landscape of possible physics. Each simulation would be a universe to its inhabitants, unaware that they exist within a computational substrate. The philosophical implications of the simulation hypothesis are profound. It suggests that the ultimate reality might be very different from what we observe. The simulators themselves would exist in some higher-level reality with its own laws and structures. That reality might be simulated as well, in an infinite regress of nested simulations. Or there might be a fundamental level, a base reality that is not simulated. But we could never know which level we occupy, or whether a base level even exists. The concept of modal realism, proposed by philosopher David Lewis, takes the multiverse to its logical extreme. It asserts that all possible worlds exist and are equally real. When we say something is possible, we mean it is true in some possible world. Necessity means truth in all possible worlds. In this view, every coherent way reality could be corresponds to an actual reality somewhere in the space of possible worlds. Our universe is just one among infinitely many, with no special status beyond the fact that it is ours. Modal realism provides a framework for understanding modality, the logic of possibility and necessity. It explains why certain propositions are necessary and others contingent. Necessary truths hold in all possible worlds. Contingent truths hold in some, but not all. This gives precise semantic content to modal claims, grounding them in the existence of concrete possible worlds. But the ontological cost is steep. Modal realism requires accepting that everything that could exist does exist. A multiplication of entities that seems extravagant. Most philosophers reject modal realism as too profligate. They prefer to treat possible worlds as abstract constructs, useful for modal reasoning but not physically real. But Lewis argued that this creates more problems than it solves. Abstract entities are puzzling in their own right. How do they relate to concrete reality? How do we gain knowledge of them? Modal realism avoids these problems by treating all worlds as concrete and real. The price is accepting an enormous ontology, but Lewis argued this price is worth paying for the theoretical benefits. In the many worlds interpretation, personal identity becomes a branching structure rather than a single thread. At each moment of branching, one person becomes many. The future contains multiple versions of you, each with their own experiences. But these versions share a common past, a single history up to the point of branching. In this sense, they are all you, different continuations of the same person. But in another sense, they are different people, inhabiting different realities and experiencing different futures. This raises questions about moral responsibility. If your actions create branches, are you responsible for what happens in all branches or only in the one you experience? If you make a risky choice that leads to disaster in some branches but success in others, have you acted wisely or foolishly? The many worlds interpretation does not provide clear answers to these questions. It suggests that traditional notions of moral responsibility may need rethinking in light of quantum branching. Some philosophers argue that we should care about all our future branches, not just the one we will experience. After all the branches are real, and all the versions of you are genuinely you in some sense. This leads to a kind of utilitarian calculus where the right action maximizes well-being across all branches, weighted by their probability or measure. But this seems strange. Should you really care about a version of yourself that exists in a branch with measure 10 to the power of minus 100? The question remains unsettled. In the level 1 multiverse, there is a limit to how far we would need to travel to find novelty. Once we have explored a sufficiently large region, about 10 to the power of 10 to the power of 115 meters across, we would begin to encounter repetitions. Beyond that point, we would start seeing copies of regions we have already visited. In a sense, the universe would repeat itself, cycling through the same configurations over and over. But the scale is so vast that reaching this limit is utterly impossible, even in principle. Light travels at just under 300,000 kilometers per second, the ultimate speed limit of the universe. At this speed, it would take light about 13.8 billion years to cross the observable universe. But to reach your nearest identical copy would take light about 10 to the power of 10 to the power of 28 years. A time span so long it makes the current age of the universe seem like an eye blink. Long before reaching such distances, the universe would have expanded, cooled, and died. Its stars extinct, its black holes evaporated, its remaining particles spread so thin that nothing of interest could ever happen again. The inflationary multiverse might have a beginning, but no end. Inflation began a finite time ago, perhaps 14 billion years ago in our bubble. Before that, there was some prior state, though physicists debate what it was. Some propose a quantum fluctuation from nothing. Others suggest a pre-existing state that transitioned into inflation. The details remain uncertain. But once inflation begins, it appears to continue forever in most of space, always producing new bubbles, always expanding, never ceasing. The multiverse is thus eternal into the future, but not into the past. This asymmetry between past and future is interesting. It suggests that the multiverse had an origin, a beginning point from which everything else flowed. This origin might have been a quantum event, a spontaneous nucleation of space and time from nothingness. Or it might have been a transition from some other state, perhaps a cyclic process where the end of one multiverse seeds the beginning of another. These questions touch the deepest mysteries of cosmology, the ultimate questions of why anything exists at all and why it takes the form it does. In the many worlds interpretation, the wave function of the universe evolves deterministically. There is no randomness at the fundamental level. Every possible outcome occurs with certainty in its own branch. Randomness arises only from the perspective of individual observers who do not know which branch they inhabit. Before a measurement, an observer exists in a superposition of branches. After the measurement, the observer has split into multiple versions, each experiencing one outcome. To each version, the outcome appears random because they have no way to predict which branch they will find themselves in. This explains the appearance of quantum randomness without introducing fundamental indeterminism. The universe is deterministic, but observers within it experience randomness because they are entangled with the systems they observe. The randomness is perspectival, arising from the limited knowledge of observers rather than from any inherent unpredictability in nature. This is one of the appealing features of the many worlds interpretation. It preserves determinism at the fundamental level while explaining the random outcomes we observe in quantum measurements. The measure problem in the many worlds interpretation asks how to assign probabilities to different branches. If all branches are real, why do we experience some outcomes more frequently than others? The squared amplitude of the wave function gives the Born rule, which correctly predicts quantum probabilities. But why should squared amplitude correspond to probability? Deriving the Born rule from the structure of the many worlds interpretation is an active area of research. With several proposed approaches, but no consensus on the correct solution. One approach uses decision theory, arguing that rational observers should make decisions as if they assign probability equal to squared amplitude. Another approach uses symmetry arguments, showing that certain natural measures on branch space lead to the Born rule. A third approach invokes self-locating uncertainty, the idea that you do not know which branch you are in and should assign probabilities accordingly. Each approach has strengths and weaknesses, and the debate continues. The measure problem is perhaps the biggest remaining challenge for the many worlds interpretation. In the string landscape, different universes could have different particle physics. Our universe has the quarks, leptons, and gauge bosons, governed by the standard model of particle physics. But other universes might have entirely different particles with different properties. Some might lack certain forces. Others might have additional forces unknown to us. The diversity depends on how the extra dimensions are compactified and how fluxes are configured. This leads to an enormous variety of possible particle physics, most very different from what we observe. Some universes might have no stable matter at all. In such universes, particles would decay immediately, preventing any structure from forming. Other universes might have matter, but no antimatter, or vice versa. Still others might have perfect symmetry between matter and antimatter, leading to annihilation that leaves only radiation. The universes capable of supporting complex structures like galaxies and life are a tiny minority among all possible universes. But in an infinite multiverse, even this tiny minority appears infinitely many times. The anthropic principle applies not just to physical constants, but to the entire structure of physics. The number of dimensions, The types of particles, the forms of interactions, all must be suitable for complexity and life. This places severe constraints on which universes can be observed. Most configurations are ruled out anthropically. We can never observe a universe where chemistry is impossible because observers require chemistry. We can never observe a universe where stars cannot form because observers require stars. The set of observable universes is thus a narrow slice of the space of possible universes. This has led some physicists to propose that anthropic reasoning might be predictive. If we can calculate which regions of the landscape are anthropically allowed, we might be able to make predictions about our universe by asking what is typical among anthropically allowed configurations. For instance, if most anthropically allowed universes have a small cosmological constant, then we should expect to observe a small cosmological constant. This approach is controversial because it requires making assumptions about the measure on the space of universes, but it offers a potential way to extract predictions from the multiverse. The ultimate fate of bubble universes depends on their properties. Some bubbles might have a positive cosmological constant, causing them to expand forever until they reach a cold, empty state. This appears to be the fate of our universe, which is accelerating in its expansion due to dark energy. Other bubbles might have a negative cosmological constant, causing them to recollapse in a big crunch. The bubble would expand to a maximum size and then contract, eventually ending in a singularity. Still other bubbles might reach a delicate balance, neither expanding nor contracting forever. Within each bubble, the processes of star formation, evolution, and death would unfold according to the laws of that bubble. Stars would ignite, fuse elements, and eventually exhaust their fuel. In universes with suitable physics, this would lead to the formation of planets, the emergence of chemistry, and perhaps the development of life. The timescales would vary depending on the constants. Some bubbles might have stars that burn out in millions of years. Others might have stars that last trillions of years, providing ample time for biological evolution. The question of extraterrestrial intelligence takes on new dimensions in the multiverse. In our universe, we have not yet detected any signs of alien civilizations, despite decades of searching. This could mean that life is rare, or that intelligence is rare, or that civilizations tend to destroy themselves before they can colonize the galaxy. But in the multiverse, every possibility is realized. There are bubbles teeming with life, bubbles where intelligence is common, bubbles where civilizations spread across entire galaxies. There are also bubbles like ours, where the question remains unanswered, and bubbles where life never arises at all. In some branches of the many worlds interpretation, humanity might survive longer than in others. In branches where we make wise choices, avoid catastrophic wars, and manage our resources sustainably, human civilization might flourish for millions of years. In other branches, we might destroy ourselves within centuries. All these futures exist in parallel, each as real as any other. The future of humanity is not singular, but plural. a branching tree of possibilities encompassing every conceivable fate. This raises profound questions about the meaning and purpose of our actions. If every outcome occurs somewhere, does our choice of outcome matter? Some argue no, claiming that the multiverse makes everything meaningless. But others argue the opposite. Your choices determine which branch you experience, and that experience is real and meaningful to you. The fact that other branches exist does not diminish the value of your own experience. You still feel joy and sorrow, success and failure. Your life still matters, even if other versions of your life exist elsewhere. The mathematical structure of the multiverse might be more fundamental than the physical universe we observe. This is the central claim of the Level 4 multiverse, the mathematical universe hypothesis. In this view, physical existence is nothing more than mathematical existence. Every consistent mathematical structure exists as a physical universe. Our universe is one particular mathematical structure, one way that numbers and equations can be arranged. Other structures correspond to other universes with radically different properties. This idea has deep roots in the history of physics. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical structures be so good at describing physical reality? The mathematical universe hypothesis offers an answer. Mathematics is not merely good at describing reality. Mathematics is reality. The effectiveness is not unreasonable, but inevitable because the physical world is a mathematical structure. But this raises its own questions. Why should mathematical structures have the property of conscious experience? Why should certain arrangements of mathematical objects give rise to observers who perceive themselves as existing in a physical world? These questions remain deeply mysterious. The mathematical universe hypothesis shifts the problem of existence from physics to mathematics. But it does not fully solve it. The mystery of why anything exists remains, now framed as a question about mathematical rather than physical existence. As you listen to these words, as your mind contemplates these vast ideas, you are participating in one small corner of the multiverse. Your thoughts, arising from the electrochemical activity of neurons, are part of the physical universe unfolding according to quantum laws. Every thought creates branches, every neural firing a quantum event that splits the world. In some branches, you understand these concepts clearly. In others, you drift towards sleep. In still others, you find yourself confused or skeptical. All these versions of you exist, each experiencing their own moment, each convinced of their singular reality. The multiverse, if real, suggests that reality is far more vast and strange than our ancestors could have imagined. We are not the center of creation. We are not even living in the only creation. We are one small part of an incomprehensibly large structure, one thread in an infinite web of possibilities. This could be seen as diminishing, a reduction of human significance to vanishing insignificance. Or it could be seen as expansive, an invitation to wonder at the creativity of existence, the endless exploration of every possible configuration of matter and energy and consciousness. Perhaps the most profound implication of the multiverse is its impact on questions of meaning and purpose. If every possibility is realized somewhere, then nothing is unique. Every choice has been made, every path has been taken, every life has been lived. Does this make our particular choices meaningless? Or does it make them more meaningful, knowing that they define which branch of reality we inhabit? The multiverse does not answer these questions. It merely reframes them, forcing us to think about meaning in a context larger than a single universe. As you begin to drift now, let these ideas settle in your mind like snowflakes falling on a still landscape. Each idea a flake, unique but part of a larger pattern. The multiverse, whether real or not, offers a vision of existence that transcends our limited perspective. It suggests that reality is not confined to what we can see or measure, but extends far beyond, encompassing every possibility, every potential, every configuration of existence. And in this vastness, you are here. One consciousness among countless consciousnesses, experiencing one moment among infinite moments. Your existence is a fact, undeniable and irreducible. You are real. Your thoughts are real. Your feelings are real. The multiverse does not change this. It merely places it in a larger context, a cosmos of unimaginable scope where every story unfolds, every question is answered, every possibility becomes actual. Rest now, knowing that in the grand scheme of things, you are both infinitesimal and infinite. Infinitesimal compared to the vastness of all that exists. Infinite in the sense that versions of you exist in endless branches, exploring every possible path. You are a wave in an ocean of possibilities, one moment in an eternal unfolding, one note in an infinite symphony. Let your breath slow. Let your muscles relax. Let your mind release its grip on these vast ideas and drift into the simplicity of sleep. The multiverse will continue without your attention. The branches will form. The bubbles will expand. The mathematics will remain true. And you, here in this moment, will rest. In the silence between thoughts, in the space between breaths, there is peace. The peace of knowing that existence is larger than you can comprehend, yet you are part of it. The peace of accepting mystery, of embracing uncertainty, of resting in the knowledge that some questions may never be answered. The multiverse is one such mystery, beautiful in its scope, humbling in its implications, forever beyond complete understanding. As you drift into sleep, imagine yourself floating in an infinite ocean of possibilities. Each wave a universe, each drop a moment of experience. You are one drop, one moment, surfing on the edge of existence. Around you stretch infinite seas, infinite horizons, infinite possibilities. And you, floating here, are enough. You are real. You are present. You are part of the eternal dance of existence. Sleep now, carried by these vast ideas into vast dreams. Let the concept of infinite universes become the infinity of your rest. Let the branching paths of reality become the branching paths of your sleep, wandering through landscapes of imagination and silence. The multiverse breathes. You breathe with it, and in that shared breath, you find perfect peace. The many worlds interpretation suggests that death itself might be different from what we imagine. When you face a potentially fatal event, the universe branches. In some branches, you die. In others, you survive through unlikely coincidences or quantum events that break in your favor. From the subjective perspective of your consciousness, you might always experience the branches where you survive, never experiencing the ones where you die. This is quantum immortality, a controversial implication of many worlds that some physicists take seriously, while others dismiss as confused thinking about consciousness and identity. But even if quantum immortality is real in some sense, it would not prevent suffering or aging. You might find yourself surviving into old age through increasingly unlikely circumstances, experiencing decline and diminishment even as you continue to exist. The concept offers no comfort and raises troubling questions about the nature of conscious experience across branches. It remains one of the most puzzling and debated aspects of the many worlds interpretation. In the landscape of string theory, the properties of each universe are determined by the geometry of the compactified dimensions. These geometries are not chosen arbitrarily. They emerge from the dynamics of the theory itself, from how the extra dimensions respond to various fields and fluxes threading through them. The process is analogous to how water freezes into specific crystal structures. The underlying laws allow many possibilities, but the actual configuration that forms depends on initial conditions and random chance during phase transitions. Some regions of the landscape might be more populated than others. If certain configurations are more stable or more easily reached through cosmological evolution, then more bubble universes might have those configurations. This could affect anthropic predictions. If our universe's properties are typical among populated regions of the landscape, we might be able to make statistical predictions about unmeasured parameters by asking what is typical in our neighborhood of the landscape. This approach remains speculative, but it offers a potential pathway to extracting testable predictions from the vast space of possibilities. The concept of eternal inflation suggests that the multiverse is always creating new bubble universes. As time passes, more and more bubbles nucleate in the eternally inflating background. The total number of bubbles grows without bound. If you could somehow observe the multiverse from outside, you would see new bubbles appearing continually, like bubbles forming in an infinite pot of boiling water that never stops boiling. Each new bubble is a new universe with potentially new properties, new physics, new possibilities for life and structure. This eternal creativity is one of the most striking features of the inflationary multiverse. It suggests that existence is not a one-time event, but an ongoing process, a continual exploration of possibility that never ends. The multiverse is not static, but dynamic, always growing, always adding new variations to its infinite catalogue of realities. This dynamism might be fundamental to the nature of existence itself, with stasis and finality being local and temporary rather than ultimate and final. The bubble universes in eternal inflation are causally disconnected, meaning no signal or influence can pass between them. Each bubble expands into its own space, separated from other bubbles by regions of inflating vacuum that expand faster than light. This causal disconnection is absolute. Even traveling at the speed of light, you could never reach another bubble because the space between you and it grows faster than you can travel. The bubble universes are isolated islands in an ever-expanding ocean, forever out of reach of one another. Yet they share a common origin in the eternally inflating background. They are all born from the same process, all governed by the same underlying laws at the highest level. The differences between them arise from how those laws manifest in different circumstances, from random variations in how the inflaton field settled and how symmetries broke. In this sense, the bubble universes are like siblings, related by common ancestry but separated by circumstances that make communication impossible. In the Level 1 multiverse, the repetition of configurations is guaranteed by mathematics alone. If space is truly infinite and the number of possible quantum states is finite, then repetition must occur. This is simple combinatorics. Given enough space, you will eventually exhaust all possible arrangements and start repeating. The distance required for repetition is enormous, but it is finite. Beyond that distance, the pattern repeats, cycling through the same configurations indefinitely. This means that somewhere in the vast expanse of the infinite universe, there are not just copies of you, but infinite copies. There are regions where Earth formed exactly as it did here, where human history unfolded exactly as it did here, where you were born and lived exactly as you have lived. These regions are separated by unimaginable distances, but they exist as surely as mathematical theorems exist. They are necessary consequences of infinity and finite possibility. The philosophical implications are dizzying. If infinite copies of you exist, then which one is the real you? All of them? None of them? The question might be ill-formed. Perhaps personal identity does not require uniqueness. Perhaps you can be multiply instantiated across space without losing your identity. Or perhaps identity is more local than we think, tied to specific configurations of matter rather than to abstract continuity across space and time. These questions remain open, challenging our intuitions about what it means to be someone. In the many worlds interpretation, the branching structure of reality is incomprehensibly complex. Every quantum event creates new branches, and quantum events are occurring everywhere all the time. In your body alone, trillions of quantum events occur every second. Radioactive nuclei in your bones decay or do not decay. Electrons in your neurons jump between energy states. Photons from surrounding light sources are absorbed or reflected. Each event spawns branches, and the branches multiply exponentially with every passing moment. The resulting structure defies visualization. It is not a tree with distinct branches that you could trace with your finger. It is more like a foam, a dense network of overlapping possibilities that blur together in their multiplicity. The measure of any individual branch becomes vanishingly small as time passes, yet all branches remain equally real. You exist in all of them, experiencing one particular sequence of events in each, unaware of the vast structure of alternative sequences that coexist alongside yours. The string landscape might contain regions that are completely uninhabitable, where the physics is so different from ours that nothing remotely like life could arise. In some configurations, space itself might be unstable, collapsing back on itself almost immediately after formation. In others, the vacuum energy might be so large that space expands so rapidly that no structures can ever form. In still others, fundamental particles might not exist in any stable form, preventing chemistry and complexity from arising. But the landscape is so vast that even if the overwhelming majority of configurations are sterile, the absolute number of life-supporting configurations remains enormous. In a space of 10 to the power of 500 possibilities, even if only 1 in 10 to the power of 490 supports life, that still leaves 10 to the power of 10 life-supporting configurations. And in the eternal inflation multiverse, each configuration is realized infinitely many times. The number of universes with life, though rare in relative terms, is infinite in absolute terms. The anthropic principle, in this context, explains not only why we observe particular values for physical constants, but why we observe any constants at all. If the landscape contained only sterile configurations, there would be no observers to wonder about the landscape. The mere fact that we exist and can ask questions about the universe implies that we must find ourselves in one of the rare configurations that permits our existence. This is not surprising. It is tautological. But tautologies can be illuminating when they shift our perspective on what needs explaining and what does not. Some physicists argue that the multiverse concept makes physics less predictive. If every possible outcome occurs somewhere, then everything is explained and nothing is explained. Any observation can be accommodated by appealing to the multiverse. Our constants have their values, because other universes have other values. Our universe is life-friendly, because we could only observe a life-friendly universe. This seems to some like giving up on the search for deeper explanations, settling for anthropic reasoning when we should be seeking fundamental principles. But others argue that the multiverse is not a choice, but a consequence of theories we have independent reasons to believe. We do not add the multiverse as an extra assumption. It emerges from inflation, from quantum mechanics, from string theory. If those theories are correct, the multiverse follows. Rejecting the multiverse means rejecting the theories that predict it, and those theories are supported by observation and mathematical consistency. The multiverse is not an excuse for lack of explanation, but a recognition that the universe is larger and stranger than we assumed. The debate over the scientific status of the multiverse continues. Some philosophers of science argue that a theory must make testable predictions to count as scientific, and the multiverse makes no such predictions. If we can never observe other universes, then their existence is a matter of metaphysics, not physics. Others argue that this standard is too strict. Many accepted scientific entities are unobservable in practice, yet we infer their existence from indirect evidence. The multiverse might be similar, forever beyond direct observation, but inferable from theories that explain what we can observe. The question may ultimately hinge on whether multiverse theories make any testable predictions at all. If they predict nothing that can be observed, then perhaps they are not scientific. But if they predict observable features of our universe, even if those predictions are probabilistic or anthropic, then they retain scientific content. The search for such predictions continues, with researchers exploring various ways that multiverse theories might be tested or constrained by data. In the many worlds interpretation, or there is no special role for consciousness in the evolution of reality. The universe does not need observers to collapse wave functions, because wave functions never collapse. Everything evolves according to the Schrödinger equation, deterministically and continuously. Consciousness is merely a physical process, neurons firing according to quantum laws, creating the subjective experience of observation, but not playing any fundamental role in the structure of reality. This removes one of the mysteries of quantum mechanics, the measurement problem, and its suggestion that consciousness might be fundamental to physics. In many worlds, measurement is just another physical process. It does not cause collapse, but rather creates entanglement between the measuring device and the system being measured. This entanglement spreads to include the observer, causing the observer to split into versions that experience different outcomes. Consciousness experiences this as a single definite result, but that is just because each version of the consciousness is unaware of the others. The removal of consciousness from fundamental physics is appealing to many physicists. It allows quantum mechanics to be a purely objective theory, describing how physical systems evolve without reference to observers or minds. But it comes at the price of accepting the reality of countless unobservable branches. Whether this price is worth paying remains a matter of debate and perhaps personal taste. As these concepts swirl in your mind, notice how they affect your sense of reality. Does the multiverse make existence seem more meaningful or less? Does the idea that every possibility is realized somewhere comfort you or unsettle you? There are no right answers to these questions. The multiverse is a scientific hypothesis, not a prescription for how to feel or what to believe about meaning and purpose. It describes a possible structure of reality, but says nothing about how we should respond to that structure. Some find the multiverse liberating. If every choice is made somewhere, then no path is foreclosed. Every possibility is explored, every potential realized. The totality of existence encompasses all stories, all outcomes, all adventures. This can feel like an affirmation of possibility. a celebration of the infinite creativity of existence. Others find it disturbing. If everything happens, then nothing is special. No choice matters more than any other because all choices are made. This can feel diminishing, a reduction of significance to mere statistical presence in an uncaring vastness. But perhaps these reactions miss something important. The multiverse does not make your experiences less real or less meaningful. The joy you feel is real joy, regardless of whether other versions of you feel sorrow. The love you give and receive is real love, regardless of whether other branches contain indifference or hatred. Your life is your life, unique to you, experienced by you, mattering to you and to those you affect. The multiverse does not change this. It merely places it in a larger context. That context might inspire awe or humility or wonder. It might make you feel small in the face of infinity or connected to something vast. It might provoke questions about identity, meaning, and the nature of existence. But it does not answer those questions. The multiverse is a framework, a possible description of how things are. What that description means for how we should live, what we should value, how we should treat ourselves and others remains for us to decide. As you drift now toward sleep, let the vastness of these ideas expand in your mind like a slow breath. The multiverse, whether real or imagined, invites us to think beyond our immediate circumstances, to contemplate existence at the largest scales, to wonder about realities we can never visit and possibilities we can never verify. This contemplation itself is valuable, expanding consciousness beyond the everyday, touching something transcendent even if we can never fully grasp it. In quantum mechanics, there is a principle called complementarity. Different descriptions of the same system can both be correct, even if they seem contradictory. Light behaves as both a wave and a particle depending on how you measure it. Perhaps the multiverse is similar. From one perspective, it is real, a genuine feature of existence predicted by our best theories. From another perspective, it is a useful fiction, a way of thinking about quantum mechanics and cosmology that helps us organize our ideas. Both perspectives might be valid in their own context. What matters is not which perspective is ultimately correct, but what insights each perspective provides. The multiverse perspective reveals connections between seemingly disparate phenomena, links quantum mechanics to cosmology, suggests new ways of thinking about probability and existence. Whether the other universes are real in some absolute sense might be less important than what we learn by considering them. The journey itself, the exploration of ideas, the expansion of imagination, has value regardless of the destination. The universe we inhabit is vast enough to occupy a lifetime of study. Galaxies stretch across billions of light years. Stars burn for billions of years. The history of the cosmos spans nearly 14 billion years. And this is just one universe, just one configuration among the countless possibilities that might exist in a multiverse. The scale is overwhelming, humbling, impossible to fully internalize. We are finite beings contemplating infinity, temporary creatures pondering eternity, local observers considering the global structure of existence. This tension between our limitations and our aspirations defines the human condition. We are born, we live, we die, confined to brief spans of time and tiny regions of space. Yet our minds can reach beyond these confines, can conceive of infinities and eternities, can wonder about multiverses and ultimate realities. This capacity for wonder, this ability to think beyond ourselves, is perhaps our most distinctive feature. It does not make us special in the cosmic sense. The universe does not care about our wondering, but it makes us special to ourselves, and that is enough. As you prepare to release consciousness into sleep, notice the peace that comes with accepting mystery. The multiverse is a mystery. We do not know if it is real. We may never know. But that uncertainty does not diminish the value of contemplating it. The questions we ask are more important than the answers we find. The wondering itself is the point. In a multiverse or a universe, under whatever laws govern existence, conscious beings emerge, who can wonder about their origins and ponder their place in the cosmic order. That capacity for wonder is a gift, regardless of what answers the wondering might reveal. Let yourself float now in the space between waking and sleeping, between thought and dream, between the particular and the infinite. You are one consciousness among countless consciousnesses, one moment among infinite moments, one point of awareness in the vast expanse of existence. And yet, you are also everything, in the sense that your existence is woven into the fabric of reality, your thoughts shaped by the same quantum processes that govern stars and galaxies, your awareness a manifestation of the same underlying principles that structure all things. The boundary between you and the universe is less clear than it seems. You are made of atoms forged in stellar furnaces billions of years ago. You are sustained by energy that traces back to the Big Bang. Your thoughts arise from neural patterns that follow quantum laws. You are not separate from the cosmos, but part of it, a temporary configuration of matter and energy that has organized itself into consciousness. When you sleep, when you dream, when you wake, you are the universe experiencing itself. One small portion of existence becoming aware of existence. In the multiverse, if it is real, countless versions of this moment are occurring. Countless versions of you are drifting towards sleep, contemplating these same ideas, experiencing variations of the same peace and wonder. Some versions will sleep well, others will wake in the night. Some will dream vividly, others will sink into dreamless darkness. All these versions are you, and all these experiences are yours, though you will only remember one branch when you wake. But for now, there is only this moment, this breath, this slow descent into rest. The multiverse recedes into abstraction as immediate sensation becomes all that exists. The feel of your body settling into stillness. The rhythm of your breathing slowing. The quiet darkness behind closed eyes. This is reality in its most direct form, unmediated by concepts or theories, simply experienced as it is. And in this simple experience, the vastness we have been contemplating finds its counterpoint. The infinite and the intimate meet in this moment of rest. The cosmos, in all its scale and complexity, reduces to the immediate present, the here and now, the simple fact of being. This, too, is part of the multiverse, if the multiverse is real. Not just the grand structures and abstract possibilities, but this moment of quiet consciousness slowly releasing into sleep. Rest now. Let the concepts fade. Let the multiverse become background, a distant echo rather than an active thought. Your mind need not hold these ideas as you sleep. They will be there if you wish to return to them, but for now they can recede, leaving only peace, only breath, only the gentle descent into dreams. In the morning, the world will seem solid and singular again. The branching structure of reality will be invisible, hidden beneath the appearance of definite outcomes and determinate facts. You will make choices that seem uniquely yours, experience events that seem uniquely real, move through a world that seems to have only one history and one future. And that is fine. The multiverse, if it exists, does not require your constant attention. It will continue regardless of whether you think about it, regardless of whether you believe in it. What matters is this: you are here, you are alive, you are experiencing existence from your particular vantage point. Whether that vantage point is one among many or uniquely special, whether other versions of you exist in parallel branches or you are the only you, your experience remains real and valuable. Your life has meaning because you give it meaning. Your choices matter because they shape your experience and affect others. The multiverse does not change these fundamental truths. So sleep now, peacefully, knowing that whatever the ultimate structure of reality might be, you have a place in it. You are woven into the fabric of existence, a thread in a cosmic design that is larger than you can comprehend, but that includes you nonetheless. Rest in that knowledge. Rest in the peace of belonging to something vast. Rest in the infinite. Good night.